Hello everyone, this is 1.5, complex numbers. Let's first recall a quadratic formula that we could have taken a look at from last section. We didn't. This one's a little bit special in the sense that, well, I guess we'll have to see when we apply quadratic formula. You can factor this as it turns out. So remember there's a 1 in front of x squared, so that a is equal to 1, b is equal to 3, c is equal to 5 for quadratic formula. So now, plugging into quadratic formula, we get negative b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. And what happens on the inside, we get 9 minus 20. Okay, inside of the radical part is 9 minus 20. The denominator is just 2. So far, so good. So now x is equal to negative 3 plus or minus the square root of negative 11 over 2. That would be the answer. There's a problem. What's the problem? The problem is a negative inside the radical. You can't have a negative inside the radical, as it turns out. And why is that? Well, it's because, notice that any number squared, any number you square will always be positive. So no matter what the number you plug into the square, whether it be a positive or even a negative number, the result will always be positive that number squared. In other words, squaring a number will always result in a positive. Only when this number is 0 is when the value will be equal to 0, but if you're squaring non-zero numbers, the result will always be positive when you square. What does that mean? Well, that means you'll never get a negative as a result of squaring. So if you want to find a number whose square root is negative 11, then what that means is if you square both sides, remember squaring things that involve radicals cancels the radicals, so you're just left with negative 11 here. Squaring x squared will give you this, but since x squared is always positive, you can never get a solution to this, as it turns out. So there are no real solutions. So let me say radical negative 11 is not a real number. Okay, more on that in a bit, but as far as this inside of the radical part of quadratic formula goes, this is called the discriminant, and let's actually see that right now. Let me just let me write it over here. So like I was saying, the discriminant, let's call it d, in quadratic formula is the part that's inside the radical, inside the square root. So it's this right here. So let's call it capital D. It's going to be b squared minus 4ac. And there are a few things we get, actually. And it depends. So there are 3 scenarios for d. The only ones we've seen so far is that d is bigger than 0. d is positive. When d is positive, the quadratic formula will yield 2 real solutions. So let me just say 2 real solutions. However, when it's equal to 0, well, think of it like this. The quadratic formula will be negative b plus or minus radical 0, which is 0. When you plus or minus 0, you get the same result. So here there's only one real solution, actually. However, when the discriminant is negative, like we saw in the previous problem, in this case negative 11, like we saw earlier, this will get negative inside the radical. It's not real, so the whole thing is poisoned, basically. So you get no real solution. And this is something, of course, we could have spoken about last time in 1.4, but we kind of ran out of time. Let me say this, though. So no real solution. We can actually talk a little more about that. What we actually get are 2 what are called complex solutions. And I'm going to describe what a complex number is right now. Let me do so over here. Okay, so now I define a complex number to be a number of the form a plus bi. I say a number. It's not a real number that we're used to, but it's composed of real numbers. And there are a few things to talk about. First off, I is a number such that I squared is negative 1. So this is not a real number. We already saw that no real number satisfies this. When you square a number, you always get positive no matter what. So I would not be a real number. In fact, I is known as the imaginary unit. And if you like, if you solve for I completely, you'll get that I is equal to plus or minus, I'll just write the plus version, the square root of -1. So I is the square root of -1, and people often think of these kinds of things as imaginary numbers, right? The next thing is that A and B are going to be real numbers. So there's what is called a real part of the complex number, and B, the thing multiplied to I, would be the imaginary part of the complex number. Okay? Now just as a quick example, let's consider the following complex numbers. 3 plus 2i, that's a good example of a complex number. I guess -3 plus or minus radical -11 all over 2 is one we saw last time. That's actually a complex number. Is it of this form? Kind of. We'll see that in a little bit. But let me just say this for now. We can split this up as to write it like this. And this is the real part. This is kind of the imaginary part. Notice it's a negative inside the radical, so we can actually change things a bit. Like this. Now all I'm doing is getting rid of the negative on the inside and writing I on the outside. And we're allowed to do that because of this phenomenon here. So let me just say as another quick example, so this is our second example, as another quick third example, the square root of -25 is the square root of 25 times -1. If you split the radical up, this is the square root of 25 times the square root of -1. Since the square root of 25 is 5 and the square root of -1 is I, this is just 5i. So very similarly here, all this is really telling us to do is you can get rid of the negative inside of the radical for an I on the outside. And that's kind of the mechanics behind complex numbers and how you can rewrite something in this form. By the way, this form of a complex number is called standard form for complex numbers. Okay? And we'll see some more examples right now. All right, so for the next thing I want to talk about when it comes to complex numbers are operations involving complex numbers. And when I say operations, I mean the four we know and love: addition, subtraction, multiplication, and division. Addition and subtraction are by far the easiest. All we're doing really is combining like terms. Think of what you would do with polynomials. Just combine things that have the same power of x. But here it's the same power of I. Notice for everything here we're going to use the fact that I squared is equal to -1. So that fact is used all the time here. So keep that in mind. When multiplying, we're going to distribute in FOIL in a very similar way we do to polynomials. But again, we use I squared is equal to -1. Division is kind of unknown. I'm going to keep that as a mystery for right now. We'll see that more after doing these problems. So here I want to do an example of addition, subtraction, and a few multiplications. So for these first few of addition, all I'm going to do is combine like terms. Simple enough. 2 and 5 are like terms. 1/2 and -3i are like terms. So all we need to do is combine those. So 2 plus 5 will give you 7. And then if you add these, well, that's going to be plus what times I? Well, as it turns out, 1/2 minus 3 is -2.5 or -2.5 or -5/2. So the answer is 7 minus 5/2 I. Now the way I did that was kind of in my head, but if you want, I'll write it here up on top. 1/2 minus 3, remember 3 is 3 over 1. So if you multiply top and bottom by 2, you get 1 minus 6 all over 2, which is indeed -5 over 2. So that's really what we're doing, but I went through the motions a little differently, but you still get the same result, -5/2, which is nice. Okay, now for subtraction, very similar story, only we have to distribute the negative before we combine like terms. So let's do that. And what do we get? We get, after distribution, 5 minus 2i, that's unaffected essentially. Double negative is +3 minus 2i. Combine like terms, 5 and 3 are like terms. -2i and -2i are like terms. Be careful, the -2i's don't cancel. They're the same sign, they're not opposite signs. So we get here for the single underlined ones, 8. For the double underlined ones, we get negative 4i. Perfect. Okay, now what? Now onwards to multiplication. Here we're going to do what, do you think? That's right, we're going to distribute. I'm hoping you shouted that out at the edge of your seat saying, distribute, distribute. That's what we're going to do. So 12i times 1 is 12i. And then minus, let's see how this works. 12 times 9, well, 10 times 9 is 90. 2 times 9 is 18. 90 plus 18 is 108. So it's 108, but we have I times I, which is I squared. What is I squared? It's negative 1. Exactly. I squared is just negative 1. So I'm going to replace it with negative 1 like this. 12i minus 108 times I squared, which is negative 1. Double negative is positive, so this is 12i plus 108. And if you're a little picky like I am, I'm going to reorder this so it's in the correct form we like, which is 108 plus 2i. Great. Now, of course, this took a little bit of space. I didn't give us quite enough space here, so let's see if we can do it in the space allotted. I think we can if we're careful enough. So let's see. It's a little harder, though, because it's not just distributing, it's foiling, actually. We have to do a double distribution. Distribute the I, the 1 first, then the I. There we go. So let's do each of these. Distributing the 1 just gives us 3 minus 2i. Fair enough. Distributing the I gives us positive 3i minus 2i squared. Remember, I squared is negative 1. Also, the middle two combined, negative 2 plus 3 is positive 1, positive 1i. So we get 3 plus I minus 2 times I squared was negative 1. We get a double negative here. So that's 3 plus I plus 2. Notice 3 plus 2 combined to 5. So what we're left with here, let me write an arrow up here, is 5 plus I for the answer for this multiplication example. Pretty good. I think that's pretty nice. Now this one is going to be fairly similar, but there's something pretty interesting that happens here. So same thing, FOIL, by distributing each one at a time. And let's see, radical 2 times radical 2 is radical 4. I'll write it out like that. It's really just 2. So keep in mind, anytime you have a radical multiplied by itself, it's just that number. So like radical 2 times radical 2 is radical 4. The square root of 4 is 2. So instead of writing it like that, I kind of lied to you. I'll just write it like this. It's just 2. Okay. Radical 2 times negative 3i is negative 3 radical 2 times I. So let me write it like that. I want to space things out so it doesn't look like the i's inside the radical, because it's not what we're trying to say. Here we get positive 3 radical 2 times I. And then finally, 3i times negative 3i is negative 9i squared. We agree, right? Because positive 3 times negative 3 is negative 9, and I times I is I squared. Notice the middle two cancel out completely because they're the same number but opposite signs. So we just get 2 minus 9 times I squared. I squared is negative 1. So this gives us 2 plus 9, which is 11. How curious. So something I haven't been quite saying, but you probably realized, hopefully you realized, any complex numbers added, subtracted, or multiplied, even divided by, or divided together, we'll see that shortly though. So any complex numbers either added, subtracted, or multiplied together will result in a new complex number. You can always write it in standard form. A plus B times I. A plus B times I. All of these can be written like that. Okay. The real interesting thing here is that you can get a scenario like we got for this last example where you multiply these two complex numbers and the result is actually a real number. It's kind of interesting. And we'll kind of see why in a second. This has to do with something called complex conjugates. Let's see if we can see that right now. Alright, so like I said, we're going to talk about a complex conjugate of a complex number. And let me just say that the complex conjugate of a complex number a plus bi is a minus bi. So you may think it's just a simple sign change of the middle sign, and you're right, but you have to make sure the order is correct. It has to be a plus bi. So for instance, just as a quick example, if you had I minus 2, its complex conjugate isn't just I plus 2. It's not that simple. You have to write it in the correct order first. So you'd write it as negative 2 plus I, then you can say its complex conjugate is 2 minus I. So it is a simple sign change so long as it's in the correct order. So if you have the correct order sorted out, then you're okay to change the middle sign. So just make sure you don't make that mistake. Also, there's a nice result here, and I say multiplying any complex number by its complex conjugate will result in a real number. So let's see that. We saw that in the previous example. We got 11, which is a real number. When we multiply those two numbers, which if you look back, they are complex conjugates, just a middle sign change. Here, let's see what happens. Let's FOIL this out in general. A plus bi times its conjugate a minus bi. Let's see what we get. We get a squared, and I guess that's minus abi, and then plus abi. And then b times negative b is negative b squared, and I times I is I squared, so it's negative b squared I squared. Good. Now what happens? Notice the middle two terms cancel out. And what we're left with is a squared minus b squared times I squared is negative 1. So what we really get is a squared plus b squared, which I'm going to box because I feel this is a pretty important fact here. You just get the sum of the squares of a and b, which is really, really nice. So let's see if we can see that in these next two examples here. By the way, now we can get to finally division. For division, what you want to do is you want to multiply top and bottom, the numerator and denominator of the fraction in question, by the conjugate of the denominator. So let's see why that is. So let's multiply top and bottom by the conjugate of the denominator, which is 2 minus 3i. It's in the right order. So there's no messing around. Just cut to the chase, basically. Good. So on top, we get some distribution, or some foiling, I should say. So we'll get, let's see, 26 minus 39i, and then that's plus 52i. Good. And then let's see, 26 times 3. What's 26 times 3? So as it turns out, it's 78i squared. On the bottom, what do we get after foiling? We get 2 times 2 is 4. That's negative 6i. That's positive 6i. And then finally we get negative 9i squared. Notice the middle two terms cancel out. Up on top, we get 26 plus, let's see, 52 minus 39 is, what is that, 13? Add 3, you get 40, yeah, it's 13i. And then minus 78 times negative 1, because I squared is negative 1, of course. Good. The bottom will be 4 minus 9 times negative 1, because again, I squared is negative 1. Great. So up on top, we get 26 plus 78, which is 104, plus 13i, all over 4 plus 9, which is 13. And yes, if you split this up, you indeed get 104 over 13 plus 13 over 13i. 104 divided by 13 is, well, let's see. I guess you can use your calculator, but I'm getting 8, just doing it in my head real quick. So that's 8 plus 1 times I. So nice. We've rewritten this weird-looking fraction of complex numbers in standard form. A real number plus a real number times I. Fantastic. Let's try for this next example. Let me kind of separate these a little bit. And let's see. So we're off to the races. Multiply top and bottom by the conjugate of the denominator. So we kind of see why we have to do this now, because it'll make the denominator a real number. Then we can split it up and write it in standard form finally. Okay, so let's see this. On top, distributing this 2 will just give us a plus 10i on top. On the bottom, I'm going to do this quickly for us. I'm just going to follow this. We're going to get a squared plus b squared. So it's going to be 4 squared plus 5 squared. You can try it on your own, but believe me, that's what you'll get. We kind of proved it. So the top is just, again, 8 plus 10i. But the bottom is 16 plus 25, which is 41. So if we split this up, it's 8 over 41 plus 10 over 41i. And no, these don't reduce. They're ugly-looking fractions, but it's still in standard form because these fractions are still real numbers, as it turns out. So there we go. Hope you enjoyed this discussion on 1.5. If you look carefully enough, there are some homework problems scattered throughout these examples, so it's up to you to figure out which ones are which. And I'll see you in the next video. See you then.